Hello, I'm Ian McCormick from Carnegie Mellon University, and today I'll be presenting on our study of undefined behavior across foreign function boundaries in Rust libraries. This work was accepted at the International Conference of Software Engineering this year, and it was co-authored with my advisors, Josh Sunshine and Jonathan Aldridge. The majority of security vulnerabilities have been caused by memory safety errors. So to avoid these errors, developers are increasingly transitioning to using languages that provide security guarantees. However, it's not going to be possible to transition all of our current applications to these languages overnight. So instead, at companies like Google, as you can see here, memory-safe components are being integrated with existing applications written in memory-unsafe languages like C and C++. So for the foreseeable future, you'll have this interoperation going on. Now, among memory-safe programming languages, Rust has been a uniquely popular choice for this transition because it can prevent safety errors without runtime overhead. Rust does this by placing static restrictions on ownership. In particular, instead of using pointers to access values like you would in C and C++, in Rust you need to temporarily borrow ownership, creating a reference. So if I'm accessing a value, I can have as many immutable read-only references as I want, or I can have a single mutable reference, but I can't use both interchangeably within the same context. If I do this, then I'm breaking the rules that Rust's borrow checker will enforce at compile time. So that'll reject my program, preventing safety issues from occurring. However, the borrow checker is inherently conservative. It'll reject certain aliasing patterns that are used commonly in C and C++ that are totally safe. So when developers need to interoperate with these languages, they need to reach for a set of unsafe features that bypass the restrictions of the borrow checker. These include accessing memory through raw C-style pointers, calling foreign functions, manipulating uninitialized memory. And in general, these features are necessary for Rust to work as a systems programming language, but if they're used incorrectly, they can reintroduce the types of security errors that Rust was designed to prevent. So we're curious, what kinds of errors are occurring in Rust libraries that call foreign functions and need to use these unsafe features to interoperate? Now we're interested in all kinds of errors here, but we're most concerned with Rust-specific issues. So Rust's borrow checker, restricts references, but developers can also use raw pointers in unsafe contexts, and these pointers behave just like they would in C and C++. This means that developers can take something, say, that Rust thinks is unique, cast it to a raw pointer, and then cast it back into another mutable borrow, effectively breaking that assumption about uniqueness there. And this is problematic because these aliasing assumptions are used to inform optimizations. Take a look at this example. The function example takes two mutable references as parameters, and from that we know that x and y should never be aliases. We could use that information to optimize the program, say by removing that extra read access through x. We know that the assignment through y shouldn't affect its value, so we could just return the constant 0. However, in the calling context, that assumption's been broken. We used an unsafe operation to duplicate a mutable reference, which is now undefined behavior, meaning that if we applied that optimization, the program might not perform as expected. Developers can find aliasing violations using MIRI, a Rust interpreter. MIRI associates every pointer with this provenance metadata, which is used to find a bunch of different classical forms of undefined behavior, like accesses out of bounds, uses after free, data races. But MIRI is also the only tool that can find these Rust-specific aliasing forms of undefined behavior. And MIRI supports two different models, two different definitions of what it means for a program to be in violation of the borrow checker's assumptions. These models are stacked borrows and tree borrows. Neither model is canonical, and both are more or less permissive in certain situations. However, MIRI has one key limitation that prevents it from being effective in the multi-language applications where Rust is being increasingly used. And that's that MIRI can't track the effects of foreign operations on the state of its aliasing model, preventing it from finding these Rust-specific forms of undefined behavior if they're triggered by operations that happen in C or C++. Without a way to find aliasing violations in these programs, it's unclear which of Rust's two aliasing models, stacked borrows or tree borrows, permits more real-world programs that call foreign functions. To answer these research questions, we conducted a large-scale survey of the Rust ecosystem. In September of 2023, we took every published Rust library and compiled them to find out which had test cases and which statically linked to foreign libraries by default. 3% of libraries had these characteristics, forming a nice convenient sample for us to analyze further. These libraries had 88,637 test cases, but not every test actually tried to call a foreign function. So we took these tests and ran them in an unmodified version of MIRI to find out which terminated due to encountering a foreign function. About 10% tried to call foreign functions that were available in the statically linked source files. So at this point, we have a sample of test cases from Rust libraries, and we know that these tests try to call foreign functions, but how are we going to be able to find errors in these tests that span foreign function boundaries? So what we did is we took MIRI and we extended it to interoperate with an interpreter for the LLVM intermediate representation that's produced by the Clang compiler for C and C++. That's how we found which libraries statically linked to foreign code. We checked which had LLVM bitcode produced for these foreign libraries during their build process. The way that our combine tool works is that MIRI controls the state of execution, as well as all operations for accessing memory. It communicates with LLI across the foreign function interface, since LLI is implemented in C++. So we took LLI, which is implemented in C++, and we found every operation for controlling execution or accessing memory, and we replaced it with a foreign function called back into MIRI, where we implemented these operations in a way that takes advantage of MIRI's state for tracking aliasing and the initialization of memory, as well as other types of errors. This allowed us to extend LLI's error detection capabilities for free without having to re-implement them in C++. We refer to our combine tool as MIRI LLI. And our goal really is not to create a production-ready solution here. It's just to create a tool that is capable of finding some of these examples of cross-language undefined behavior so we can examine their characteristics and have insights into what leads developers to make these mistakes. So we took our tool and we executed all of the test cases that we found, and the majority found some operation that our interpreter didn't support. However, 9% did have what we'd consider to be a potential bug, so an instance of undefined or undesirable behavior. So we took all of these individual test outcomes, and then we deduplicated them into 394 unique outcomes to manually investigate it. Our deduplication process involves finding execution-specific identifiers, like the borrow tags and addresses shown in the error message below, and then removing them so that the content of the message would be the same across test runs. And our method was really successful. We found 46 different instances of undefined or undesirable behavior from 37 different Rust libraries. At the moment, 28 of these bugs have been confirmed and fixed. Though the majority came from libraries that had less than 100 daily downloads during our observation period, we found 3 with more than 10,000 daily downloads, including one from a library maintained by the Rust project. Now, we classified these bugs in multiple ways. First, for location, we consider the location of the fix, which we applied in many cases, and the error. So this included at the foreign function bindings in Rust, within LLVM, or within Rust. We also identified 3 different bug types based on the characteristics that we saw in these bugs. Allocation includes mostly memory leaks, though we did find one instance of cross-language deallocation. Ownership includes accesses out of bounds and aliasing violations, and then typing bugs typically involved initialization with Rust-specific types like maybe on the net. Now, what's important to note here from this table is one particular category of bug. Take a look at this row. The most common type of bug involved ownership violations, and these bugs were fixed in Rust but occurred in LLVM. Now, all of these bugs had some meaningful cross-language interaction, but what this highlights in particular is that aliasing violations exist in multi-language libraries in practice. So this clearly answers our first research question. We found a variety of different errors that occur in real-world multi-language libraries. But what about Rust's aliasing models? So in this particular table, we're only considering tree borrows violations, but we did run every test case under stacked borrows too. What we found is that of the tests that had a stacked borrows violation, most did not have a tree borrows violation. There were several reasons for this, but the most common pattern that we observed involved the valid range of a reference. So in stacked borrows, when you create a reference, it's only valid for the range that it borrows. So if I create a reference to the first element of an array, I can't do any pointer arithmetic and offset that to adjacent elements because that pointer won't be valid for those other elements. It's only valid for the first one. However, under tree borrows, the range of a reference can be lazily extended across the entire allocation. We'd see a lot of cases where a reference was created, passed from Rust into C, and then offset in C, but it wouldn't be valid for any of those adjacent locations under stacked borrows. So we've answered our research questions here, and there are many different bugs that we found, plenty to focus on with different characteristics. But there's one that does a really great job of illustrating the difficulties of interoperation and why we feel that it's going to be crucial to be able to find these aliasing violations in practice in multi-language programs. We found this bug in a Rust encapsulation for an embedded file system implemented in C. So the first step to using this library from Rust is to create a file system object. Then, for a file, you need an allocation, and to hook that allocation into the file system, use a file object as sort of a handle. Now, this aliasing pattern seems fine at first glance. There aren't any major red flags here. But remember, there's some C happening beneath the surface here. When the file gets created, a mutable reference to the allocation is copied across the foreign function barrier into C as a pointer. That pointer is then stored within a linked list within the file system. And this has created a situation that will lead to an aliasing violation, right? Because we have that mutable reference over in Rust that Rust can think is unique, but it's possible to mutate that allocation through the file system as well. This leads to a situation where mutating the allocation through the file then causes that pointer held by the file system to be invalid, leading to a cross-language aliasing violation. We found this bug in a few test cases, but we didn't observe any miscompilation. So why should developers care about this type of bug, right? I mean, you could dismiss it as a false positive since it doesn't seem to have any effect on the semantics of the program. In an earlier version of this library, it was possible to drop the file and then drop the allocation, freeing both of these, and that left a dangling pointer within that file system object, leading to a use after free error. Now that bug has been fixed, and it was fixed before we even started the evaluation, and we've since fixed the aliasing violation. But our hypothesis is that if developers had been able to find that aliasing violation earlier, it potentially would have led them to finding the use after free error as well, because it involves that same aliasing pattern that conflicts with Rust's expectations. This is why it's going to be crucial to be able to find these aliasing violations in practice in these types of libraries, both to avoid situations where optimizations break the semantics of the program as written, and in these situations where breaking Rust's aliasing rules makes it possible to trigger other more severe forms of undefined behavior. Now, we're going to make it possible for developers to find aliasing violations in large-scale multi-language libraries with Borrow Sanitizer. This is our work-in-progress tool, and similar to Address Sanitizer or Thread Sanitizer, it's an LLVM-based instrumentation tool for finding violations of Rust's aliasing model in applications where Rust is used alongside C and C++. We've had several collaborators join us for this project too. Oliver and Johannes have joined from Ludwig Maximilian University. Aaron was here this past semester helping us, and then Raphael joined us this summer. Borrow Sanitizer isn't functional yet, but we aim for this to be a production-ready solution integrated with the upstream Rust toolchain. You can follow our development updates at borrowsanitizer.com, where you'll also find links to our GitHub organization and our Zulip channel. So we conducted a large-scale study of undefined behavior across foreign function boundaries in Rust libraries. We had 2 research questions. We were curious what kinds of errors occur in practice, and which of Rust's aliasing models permit more real-world programs with foreign function calls. To answer these questions, we conducted a large-scale study, compiling every crate to find test cases that called foreign functions. We ran these test cases in MiriLLI, a prototype tool that can find aliasing violations across foreign function boundaries. We used our tool to find 46 different instances of undefined or undesirable behavior from 37 libraries, including one that was maintained by the Rust project. In our future work, Borrow Sanitizer We'll be creating a production-ready tool for finding these aliasing violations at scale. Thanks for your time and interest. You can find links to our preprint, our artifact, which is hosted on Zenodo, as well as Borrow Sanitizer, both here and in the description of the video.